Hi there. So thanks for listening in. This presentation is going to focus on a topic that's near and dear to my heart, which is the study of planetary rings. Now, when you think of rings in our solar system, the planet you most likely think about is Saturn, and this is for good reason. Saturn has the most extensive and, in some sense, the most beautiful example of a ring system, and it's something you can see even through a small telescope. But it's important to understand that while Saturn's rings are unique in how extensive they aren't unique in the solar system. In fact, every single one of the giant planets has rings. These are pictures of all of them taken by various spacecraft. This is a picture of Jupiter's rings taken by Galileo. This is a picture of Uranus's rings, which are obtained actually from the ground. This is a nice picture of Neptune's rings obtained by the Voyager spacecraft. So rings seem to be a common part of giant planet systems. And they're actually even more common than that, because in the last decade or so, people have discovered rings around smaller objects. Now, to date, nobody has found rings around anything in the asteroid belt, but there's an object out in the Kuiper belt called Haumea, which has narrow rings, and there are also rings around some of the larger asteroid-sized objects that share orbits with the giant planets or orbit in their vicinities, which are known by the names Chiron and Carita. So rings are at least a common feature in the outer solar system. But at the same time, they're actually a fairly diverse collection of objects. What we will learn is that these are actually systems of many, many small bodies, but the way those bodies are distributed can vary radically. For example, the amount by which light can get through a ring can vary by orders of magnitude. One nice illustration of that is this picture, which shows the rings passing in front of Saturn. This ring, which is known as the C ring, you can see Saturn through it quite well. It only blocks about 10% of the light passing through it. By contrast, this ring, the so-called B ring, blocks over 99% of the light coming through it. You can't see the planet behind the rings at all. And in fact, this ring is casting a shadow on the planet. So rings vary dramatically in terms of their opacity. They also vary dramatically in terms of their composition, which we can see by looking at how they reflect light. Part of the reason Saturn's rings are easy to see even with small telescopes is that they are broad. But it's also easy to see them because they're very bright. They're reflective. They reflect about half the light incident upon them. They're as bright as newly fallen snow, basically. By contrast, the rings of Uranus are hard to see, in part because they're particularly narrow, but also because the material in them is as dark as charcoal. And this reflects fundamental differences in their composition. The rings of Saturn are made primarily of water ice, whereas the rings of Uranus seem to be made primarily, or a large fraction, of carbon compounds. So there's a lot of diversity in these ring systems. And because of that, rings are given a bunch of different names. Now, not expecting you to memorize these, I'm just going to say, be aware that the naming conventions for rings is a little weird. In Saturn's rings, they're given letter designation more or less in order of discovery. So the A, B, and C rings were seen first, then the D, E, F, and G rings. The Uranian rings are either designated by numbers or Greek letters. The Neptunian ring system, these rings are designated by the name of scientists who are involved in the discovery of Neptune itself. And Jupiter's rings are actually given descriptive names like the main ring, the halo, and the gossamer. Now, there is a lot of diversity here, and given an opportunity, I could spend an entire time talking about any one of these rings. But for the sake of conciseness, we're going to focus here on some common aspects of ring systems, which are important for understanding how rings work. So, first of all, we're going to talk about the fact that rings are not solid objects, they're composed of many small particles. Then we'll talk about how flat the rings are, and in fact, how remarkably flat they are. And then we'll talk about where rings tend to be situated. That is, they tend to be found close to their host planets. And finally, we'll talk about how a lot of the structure of the rings is sculpted by interactions with the moons. Okay? So let's first talk about this fact that the rings are made out of many small particles. What is the evidence for that? We actually don't have pictures of the rings at high enough resolution to really show that. The evidence we have that the rings are not a solid disk of material comes from studying how the rings move. So imagine we had a solid disk of material that was just spinning around the center of the planet. Well, if that's a solid disk, the outer part of the ring has to go a bigger distance than the inner part. So the outer part of the ring would move faster than the inner part, if you could measure that. On the other hand, if the ring was composed of a bunch of particles in orbit around the planet, particles on the inner part of the rings are closer to the planet. So by Kepler's laws, the particles closer to the planet would move faster than the particles further out. And the thing is, we know how to measure motion. Even if we can't resolve things, we can use Doppler shifts to measure how fast these various parts of the rings are moving relative to us. And this was in fact first done over 100 years ago in 1895 by a guy named Keeler. He measured the spectra of the sunlight bouncing off the rings, and he was able to make this plot, which shows the red shift and blue shift of the light as a function of distance across the rings. So the bigger the red shift or the bigger the blue shift, the faster the motion. And what you will see is that the outer part of the ring is moving ever so slightly slower than the inner part. This is inconsistent with the rings being a solid disk, but is instead consistent with them being composed of many particles in orbit around the planet. And this is our standard picture now. And is why you see lots of artist renditions of the rings that look like this, with lots of particles just in orbit around the planet. And with more up-to-date studies, we even have a sense of the size of these particles. In Saturn's main rings, they range in size between millimeters and meters in sizes. So we're talking pebbles to houses. And this is the kind of picture you find quite often in textbooks. This picture, though, is very inaccurate. The problem with this picture is that the particles are too spread out. If you imagine like these big particles we're seeing are about the size of houses, then some of these particles are up to 1 kilometer away from the ring plane. And we don't think the rings are that vertically extended. This brings us to the second point about rings. Dense rings like the ones around both Saturn and Uranus are extremely flat. Now, you can start to get a sense of that from just looking at images taken at different perspectives. From the ground, you can take pictures of Saturn's rings as from a variety of angles. And when the rings are edge on, this vertical thickness is set by the resolution of the camera, not by the vertical thickness of the rings themselves. Similar pictures can be taken of Uranus. And again, what you're seeing here as a vertical thickness is just the resolution limit of the camera. And even if we get close up, this is a picture from the Cassini spacecraft, that vertical height is still just set by the resolution of the camera, not the physical width of the ring. The current best guess for the vertical extent of the rings is of order a few meters. That is comparable to the size of the largest particles. So it turns out that the rings don't look like this, where if you're standing on one particle, there might be some above or below you. They instead look like this, where all the particles are in basically a single layer. This is, again, a very alien environment. If you were standing on one of these ring particles, there'd be almost nothing above you. Below the particle you're standing on, there wouldn't be much going on. But you'd see particles in an infinite horizon surrounding you. Now, at first, this might seem very contrived, but in fact, this is the natural configuration for a ring to get into. And the reason for that can be understood by thinking about what a ring like this requires. It's natural when you look at something like this to think that the ring particles that are above the ring plane are just staying there. But that's actually not possible, because if a particle was always above the ring plane, its trajectory would look like this. That's not allowed by Kepler's laws. Remember, the center of the orbit needs to be one of the foci of the ellipse, or if it's a circular orbit, it needs to be the center of the circle. This sort of levitated orbit just doesn't happen. If you want something to go above the rings, it can't be offset, it has to be tilted. So a particle that is above the rings is actually slowly drifting up and down. Sometimes it's above the rings, sometimes it's below the rings. So if you have a ring like this particle is going to come down through all of these other particles, and these particles near the bottom are going to move up towards other particles. What does that mean? They're going to run into each other. There are going to be collisions. So these particles are not moving very fast. Relative to each other, they're moving at speeds of order centimeters per second or millimeters per second. So slow walking speed. These collisions aren't disruptive, so they're not going to break apart, they're going to bounce. But these are snowballs, they're not superballs. So they don't come out of that collision moving as fast as they did when they came into it. So these particles moving up and down will bounce off each other, but since they come out moving at a lower speed than they went in, that's going to damp their vertical motions and damp how far they can get away from the ring plane. Those collisions therefore take that vertical motion and dissipate it, turn it into heat. Turning these ring particles that was dispersed vertically, this will naturally evolve into something that is very close to a single layer. And the time it takes to do that is basically set by how long it takes the particles to go around the planet, which is a matter of hours to a day. So this happens relatively quickly. Now, this also might lead to a question. Well, wait a minute. If collisions dissipate relative motion, shouldn't these things clump up eventually, forming moons? And that's a reasonable thing to ask about. And it turns out that the reason that doesn't happen has to do with where this ring material is found. All of these rings that are relatively dense with lots of mass are found close to their host planets. That's why they can be seen in these nice dramatic pictures of the various planets. That's not a coincidence. Ring systems naturally occur close to their host planets. To understand why, let's consider a simple cartoon. Imagine we have a planet here, shown in orange, and we have two particles in orbit around it. One happens to be a little closer to the planet, one happens to be a little further away. These particles are on an orbit that goes from top to bottom. And we're going to ask, do those two particles orbit the planet separately, or do they stay stuck together? Now, there's two different forces involved in this question. The two objects have mass, so they have gravity. And that mutual gravitational attraction will tend to hold them together. However, since one of those particles is closer to the planet than the other, by Kepler's laws, one of them is moving a little faster than the other. So that is going to pull them apart. So the mutual gravity of the two particles wants them to stay together, but their gravitational interactions with the planet tries to pull them apart. And the question is, which one wins? And the answer to that question depends on where these particles are. If the particles are far from the planet, like here, then the difference in the speeds at which the planet is pulling on them, or the difference of the strength of the forces of the planet pulling on them, is smaller. The difference in their preferred orbital motion is less. In this case, the mutual gravitational attraction is strong enough to hold them together, so they'll orbit the planet together. By contrast, if we bring those particles closer to the planet, the difference in their preferred orbit speed increases. The tendency of the planet's gravity to pull them apart increases, and it is high enough to pull the particles apart. And so they orbit the planet separately. This is more like a ring. So the space around a planet is naturally divided into two zones. There's a region close to the planet where rings tend to live, and a distance further from the planet where particles can clump together under their own gravity, which is where moons tend to live. And there is a critical distance from the planet that separates these two zones, which depends on the size of the planet and the density of this material. Not expecting you to know what this formula is. I'm just saying that the existence of this specific distance is something you can calculate. It's something called the Roche limit. And you can calculate this for any planet and for material of any type. And it turns out if you calculate that for things you expect to be in orbit around these planets, it actually works quite well. These blue lines indicate the Roche limit for these different planets. And what you will see is that that Roche limit basically contains all of the observed ring material. Now, one thing I do want to say is don't overinterpret this limit too much. Don't think that something crossing that limit instantly goes from being a moon to being a ring particle. This calculation assumes the only thing holding the object together is gravity, which isn't true. For example, we're inside the Roche limit for Earth, but we're not being pulled apart by the Earth's tidal forces because we're not held together by gravity. Humans are held together by chemistry, molecular bonds, which are much stronger than gravity. Similarly, small moons and boulders are held together by basically the bonds that hold ice together. That's still chemistry, not gravity. So what that means is these boundaries are in practice kind of fuzzy. And near their edges, near this Roche limit, moons and rings can coexist. This is a close-up of the outer part of Saturn's rings. And you can see there's a ring here outside the orbit of the moon. And here we have a moon orbiting inside the rings. So there is a kind of fuzzy boundary here. So moons and rings can coexist, especially near the Roche limit. And this serves to illustrate something else, that moons and rings interact in very interesting ways to produce structure in rings. One thing to say is rings have a lot of structure in them. We already talked about how there's different parts of Saturn's rings called the A ring, the B ring, and the C ring, but even within these rings, you see a lot of structure. And to be honest, we don't understand what causes most of this structure. It seems like particles are gathering in certain regions and avoiding others. And to be fair, we still have very little idea why this is the case in many parts of the rings. There are a few places where we do have an understanding, and it usually involves interactions with various moons. Particular in the outer part of the A ring, there's a gap here. And if we zoom in on that gap, we will see that there is a moon orbiting in the middle of that gap. This is the moon called Pan. This gap is called the Encke gap. There's even a narrower gap out here called the Keeler gap, which has within it a moon called Daphnis. So there's a clear thing going on here. The moons seem to be producing a gap. But the key thing to notice is that gap is bigger than the moon. So it's not like the moon is just plowing through material and pushing it out of the way. The moon is affecting the ring material at a distance. It's keeping material away from its orbit at some distance. Now, the only way that a moon and a ring particle can interact at such a distance is via gravity. So the going explanation for what's happening here is that the moon's gravity is causing the ring material to be pushed away from the moon's orbit. This is called gravitational shepherding. And this is seen elsewhere too. We have narrow rings at both Uranus and Saturn, which appear to be shepherded by small moons. Now, all of these examples are weird if you first think about it, because it's like, wait a minute, gravity is an attractive force. Shouldn't moons pull ring material towards them? Why is it creating a gap? Why is it pushing material away? Well, to see what's going on here, it's useful to again consider a cartoon example. Let's say we have a planet here and we have a moon following this orbit. And then we have two ring particles on either side. And we'll just look at two. This one's following this orbit, this one's following this orbit. Now, this particle is a little closer to the planet, so it's moving a bit faster. This particle is a little further from the planet, so it's moving a little slower. So there'll be a time when the moon catches up with this particle and this particle catches up with this moon. At that point, these particles are as close to the moon as they ever can get. So they should feel a little extra gravitational tug towards the moon, which means that they should be deflected onto trajectories that bring them in towards the orbit of the moon. That makes sense. The thing is, you can't stop there. because these three objects aren't just moving through space, they're in orbit around a planet. And you can't ignore the planet's presence in this calculation. The thing to understand is these particles aren't just following trajectories, they're following orbits around the planet. Now, before they encounter each other, we can say they're initially on circular orbits. So they all stay roughly the same distance from the center of the planet. The encounter changes those orbits. It initially pulls the particles so that they're moving either outward or inward. But a radial motion means we're no longer on a circle. We must be on an ellipse. The planet remains at the focus of that ellipse. So what that means is that while the particles originally move in towards the orbit of the moon, a bit later, as they keep going around, they'll move further away from the planet. Sorry, they'll move further away from the orbit of the moon. So this inner particle initially moves out, which brings it closest to the orbit of the moon, but then it moves in away from that orbit. And so it oscillates back and forth. And in fact, we can see this in the rings. This is a picture of that Keeler gap. Here's Daphnis. This is the material that is drifting by that is just drifted by the moon. And it does get pulled towards the orbit of the moon, but then oscillates back and forth, back and forth. Now, if you do the math carefully, very carefully, what you will find is that the average of all of that motion has actually displaced the average position of the orbit away from the moon. It's like you get pulled one step forward, but then get pushed one and a small fraction back. So it's basically to show that the interactions between objects, even gravitationally, can be quite complex, especially if they're in orbit around something else. Just to say, we see all sorts of interactions like this. This is a case where we have a discrete moon producing a gap, but we also now see structures like this just in the ring. The impression being there's a larger than average ring particle trying to do the same thing, but which just isn't able to open up much of a gap. Now, just to say, there are other structures in the rings produced by interactions with other moons. In addition to these gaps, there's this very sharp edge to the rings. And there's also these features which we call density waves. These are also produced by interactions with moons, but not by nearby moons, but very far distant moons. These are things produced by resonances. That is, places where the orbit period of the ring particles is an integer multiple, a place where the orbit period of the ring particles is a whole number ratio times the orbit period of one of the moons. So for example, here is where the orbit period of ring particles is about 6/7 the orbit period of Janus, which is one of Saturn's moons. This is something that is also relevant for the geologic activity on moons, and so we'll talk more about that in the next presentation. Okay, so I've now shown you a bunch of things about these rings that I think are fairly universal. A very natural question to ask is, where did this come from? How old are these systems? And that's actually something that is now being addressed, or at least thought about very hard. Now, the answer depends on which rings you talk about. For Jupiter and Neptune, most of the ring material seems to be of very fine particles, the size of dust. Those sort of particles only last for about 1,000 years before they're basically destroyed by radiation or micrometeorite impacts. So those kind of rings need to be constantly be generated by impacts into larger bodies. The rings of Uranus and Saturn, by contrast, are composed of particles between millimeters and meters in size. Those particles could potentially last the entire age of the solar system in orbit around a planet. So it's natural to ask where these things came from. And at the moment, that is a question we really want to have answered. And it's something we are starting to come to grips with for Saturn. The question can be phrased as, how long has Saturn had rings? How long has it looked like this? Now, there's a really good, besides just kind of wanting to have a number for textbooks, this has important implications for how things like rings form. Because is rings part and parcel of how planets form? Like, do giant planets just naturally form with rings? In which case the rings would be 4.5 billion years old, like everything else in our solar system. Or are they something that happens more recently? People have proposed that the rings formed late when something got too close to Saturn and basically broke up. It got in, something took material that was outside the Roche limit, pushed it in, and it got torn apart to form a ring system. Which of these is correct? Well, what we need to do to answer that question is figure out how old the rings are. And that's not something you can answer by like saying, let's get a sample of ring material and measure its age, because we don't need to know how old the material is. We need to know how long it's been in this particular state. That's a tricky question to answer, but we've gotten some information about it. And it's based on a study of the composition of the rings. The rings are really, really, really just water ice. They're 99% water ice, which is unusual. Most things in the outer solar system are not that pure or simple in their composition. If we looked at, say, comets, comets are about half water ice, half other things, carbon compounds, rock, etc. Now, the rings could have formed differently from other bodies in our solar system in a way that just made them pure ice. But those rings are constantly being hit by comets, which are made out of not ice. So over time, comets should pollute the rings and make them not just water ice. They haven't done that yet. So that tells us something about their age, ideally. But to do that, we need quantitative numbers. We need to know how much material is in the rings, and we need to know how much stuff is crashing into them. Now, we do know both of these numbers, though. We know the mass of the rings in a couple of different ways. One of the most dramatic ways of doing it was by flying the Cassini spacecraft between the planet and the rings. So the planet's pulling it in one direction and the rings are pulling it in another. That allows you to tease out the mass of the rings. And the number you get from that is, with a fair degree of uncertainty, about 10 to the 19 kilograms. So that's a pretty big number. We have also been measuring the flux of material into the rings. There are observations of clouds of debris kicked up by impacts. There's also an ability to measure micrometeorites crashing into the Cassini spacecraft. Based on those sorts of observations, we can say that about 10 kilograms of debris crashes into the rings every second, or about 5 million kilograms strikes the rings every year. Those are the numbers we need. We can say, okay, the rings are of order 2 times 10 to the 19 kilograms. Only 1% of that is not ice. So only 2 times 10 to the 17 kilograms of non-icy material can be added to the rings. If 5 million kilograms hit the ring every year, and about half of that material is not ice, then we're adding about 2 million kilograms every year. That means it would take 100 million years to add 2 times 10 to the 17 kilograms of non-icy material to the rings, which suggests that the rings are only 100 million years old, because if they were any older than that, they would have a larger non-icy fraction. This would support the idea that the rings are much younger than Earth's moon, asteroids, or most other objects in our solar system. So the rings are a recent addition to Saturn, not something that's been around since it formed. Now, these are still an area of active scientific discussion. People are going, well, maybe there's something that removes the non-icy material from the rings and allows you to go around this. This is an area that's still very actively being discussed, and new arguments and thoughts about this are happening all the time. But that is what I plan to cover on rings in this presentation, and thank you for your attention.